this morning we're going to look at inverse functions. We've been taking a look at functions and their domains. We've taken a look at the reflections of equations and how we can take graphs and reflect them over different axes, y equal x line, we can reflect them over a point. So we're going to specifically focus in on the inverse function, which is going to be a reflection over y equal x. Now, what is an inverse function? A great example to talk about the concept of inverse function is looking at the equations we have for Fahrenheit and Celsius, the conversions between our two different degree systems. In Fahrenheit equation, Fahrenheit becomes our dependent and Celsius becomes our control. And then in the converted formula for Celsius, we swap roles, and the Celsius becomes the dependent and Fahrenheit becomes the control. So if we were to take the first equation and plug a 0 in for the control variable c, we would find that f would equal 32. And if we did the same concept thinking about Celsius, if we put the control variable f, we put a 32 in for that, then we would get a c value equal to 0. So what's happening is our dependent and our control variables are swapping. And one equation is undoing the other one. So that is the concept of an inverse function. We'll take a look at it algebraically. We'll also take a look at it graphically. All right, here it is. You will have a fun times question. Deals with proving or showing that two functions are inverses of each other, and the method by which you will be doing that is to take their composites, plug one function into the other, and then each time I do that, I'm going to hopefully get a result of x. So this is what I'm going to be looking for if I say, tell me the two functions are inverses of each other. We have function f and function g. We composite f into g, so g of f of x. We get a result of x. Then we switch the roles, and now we composite g into f. So f of g of x. We also get an x. Then we have two inverses. So we're going to see an example of that here in just a little bit. The function notation for inverse is denoted by f to the negative first power. And don't get this confused with f to the negative first of x equaling a reciprocal, because they are not reciprocals. You actually have, on your calculator, you probably have a button that looks like that, or it might even look like this. Those are reciprocal functions on the calculator, not inverse functions. So please don't get them confused. F to the negative 1x is what we will use to say I've got an inverse of x. What do the graphs look like? Well, we've actually already played around with this a little bit when we were taking a look the other day at graphing anything and seeing what the reflection looks like. We found that we can reflect over a line y equal x. I'll always be able to take any graph and reflect it, but the reflection of the original function may not be an inverse, meaning the reflection isn't a function, it won't pass the vertical line test. That's what we're thinking about graphically, is does our reflected graph pass the vertical line test, indicating it is a function as well as the original. So here we are with function notation y equal f of x, and we've got some coordinate on our graph, AB. If I have the inverse, graphically speaking, what that means is I can just swap the coordinate values of the original function, AB, and they now become BA. And we saw that in the example with Fahrenheit and Celsius. The Fahrenheit and Celsius roles swapped when we went from one equation to the other. So this is probably the easier way to graph these reflections, which are inverses, is to just, if I know the original function coordinates, we can just swap them. The other way is sometimes our inverse functions will be a parent function that we're familiar with, and we can graph just from the parent function information as well. All right, let's try this stuff. Let's take a look at just this concept of swapping roles. So here we have f of 12 equals 43. And remember what that is a coordinate. We've got 12, 3 on some graph, some original function. And now we're going to go find the inverse function's equivalent point. So 1243. And if the inverse says, so again, there's the inverse notation. Inverse says, let's swap their roles. Well, now in this inverse notation, I've got inverse of 43. So what I've done is, what was the y value? 43 has now become the x value of this function. And so that means if the 43 has become the x, that must mean that the 12 must now play the role of the dependent variable y. So I'm just swapping the roles. Inverse of 43, I'm thinking, let's put the y value in the x spot. And then we can keep expanding on this. What if we have a function of an inverse, or an inverse of a function, as in the case of b and c here? This is just the concept of recognizing a point and swapping our values. And we'll take a look algebraically at what's going on when we rewrite the equation for these inverse functions. So let's work inside to out for b. So I'm going to take care of the inverse of 43. We did that in part A. We know that that is already equal to 12. So what we're going to do is we're going to rewrite this as f now of 12. So now we're back to this function notation of an original, and we're taking that value from an inverse. So we go and we think, all right, what is f of 12? Well, we already know, based on what was given to us, for the coordinate 12, 3, that f of 12 is equal to 43. There's the x role, there's the y role in our function notation. What about c? Again, working inside out. So taking a look first of all at what is f of 12. Well, we just found that in the problem above. Here's f of 12. Or also, it's in the original problem. So f of 12 we know is already equal to 43. So the f of 12 spot goes there. And now we're taking the inverse of 43. Well, that's pretty much what we just did up here at A. The inverse of 43 would be equal to 12. So it's just a matter of recognizing that you're switching the roles of the coordinates when you're talking about inverses of a point. Pretty simple concept. Once we start to build functions within functions or inverse functions within functions, you just have to be keeping your wits about you. Again, always working from the inside out. You're talking about these inverse function notations. All right. Let's roll the next one. Some FYI here. So if a function y equal f of x has an inverse, that function will be called a one-to-one function. One value of x to one value of y. And a very quick way of us testing whether the original function has an inverse is to use our horizontal line test. We are already familiar with vertical line tests, and vertical line tests, VLTs, they test for whether or not something is a function, and meaning does it have that one-to-one relationship. The horizontal line test will tell you what kind of function you have. One-to-one, many-to-one. We're looking for one-to-one functions, because that means if it's a one-to-one function, I will have an inverse. I will be able to generate a rule or an equation for the inverse, and I will also be able to generate the graph for the inverse. So I determine, yes, horizontal line test is passed for some given function. So to find that equation, we switch the x and y's, and then we resolve for y. So this is the new component compared to what we were doing yesterday. Yesterday we were just doing the graphing piece of it. Now we're going to take a look at the switch the x's and y's and solve for y. We've already done this in Algebra 2, so it's not new. So we'll just be doing a little review, and then there are some functions, though, that we have to be careful with, and those are the ones that have what we call a restricted domain. Thinking about our parabolas, that's not a one-to-one. If I did a horizontal line test on a parabola, for example, just real quickly, let's just sketch a parabola in here. Horizontal line test on a parabola, it doesn't pass. We hit the function twice. But instead, if I just only looked at half of the parabola, now I pass the horizontal line test. And with these cases, we're going to have what's called the restricted domain. We're forcing the issue. We're forcing this to become an inverse. Right, we're going to get to that though in just a second. All right, in this book, this text uses the word rule. It says find a rule. And rule just means we're looking for the equation. We're looking for the equation of the inverse function. So that's what the rule is going to refer to. So we're going to state whether or not the given function has an inverse. And it would help if we remember what the parent function looks like. We've got a visual in our head of what these graphs look like. And if not, we can sketch them real quick and see. And if there is an inverse, if it exists, we're to find this rule or this equation and show that the composites of the original function and the inverse both equal x. So there's that proof that two functions are inverses of one another, is that we composite them, and then we get an x both times. All right, for A, for example, quick sketch on A, we know that the parent function is y equal the absolute value of x. And in a sketch, we would know that that graph is a v. However, with this notation x plus 1, what that means is we have shifted. It's a translation. We're going to go left 1 with our graph. So we're going to move over one spot. And then we're going to go ahead and do our, in this case, it's a one slope, but a negative 1 slope from that point, and we get that graph. Again, if I don't remember my parent function, safety net, put in a t-table of values, pick your own x's, find your y's, generate the graph, get a quick idea so that you can do your horizontal line test. And in this case, we recognize that I do not pass the horizontal line test, and therefore, I will have no inverse for this function. Even though I could reflect that graph over y equal x. So here's my y equal x line. And if I took all of the coordinates of that v and I switched them, my x's became y's, negative 1, 0 becomes 0, negative 1. And then 1 or 0, 1 becomes 1, 0. And negative 2, 1 becomes 1, negative 2. You can see that I'm going to generate a sideways looking v. And that sideways looking v, if I wasn't paying attention and I ignored the horizontal line test, if I did the reflected graph, I would recognize that that reflected graph does not pass the vertical line test, and therefore is not a function, and therefore is not an inverse. So I always have some backup if I don't remember the horizontal line test stuff. Generate the reflection. Does it pass vertical line test? If not, then it has no inverse. So we're not going to worry about writing a rule for that one. B, a reciprocal function, f of x equal 1 over x plus 1, where x does not equal negative 1. Now, this is not a domain, well, I guess it is a domain restriction, but it's kind of it's a necessity here. The reason I can't equal negative 1, because if I did put a negative 1 in there, I'd have a denominator of 0, which would make this undefined. So what this is this is telling you what one of your vertical asymptotes. Sometimes you have more than one. So we have a vertical asymptote at x equals negative 1. Horizontal asymptotes, again, thinking back to our Algebra 2 days, is a quick way of deciphering what our horizontal asymptotes are. If the degree of your numerator is smaller than the degree of my denominator, so that's, up here we have a constant, so it has a degree of 0. And then this is a linear function, so it has a degree of 1. And when the degree on the numerator is bigger than the degree on the denominator, we have a horizontal asymptote. That is going to be 0. So when y equals 0, we have a horizontal asymptote. The other rules, when your degrees of the numerator and the denominator are the same, then you're looking at the coefficients, the lead coefficients, and you're coming up with a slope there. Technically, what we would do is actually think about long division and find out the remainder would become our equation for our slanted asymptote. And when the degree of the numerator is bigger than the degree of the denominator, you have no horizontal asymptotes. All right, so graphically, what does this thing look like? Again, a quick sketch. We have our axes here. Let's go ahead and put in our asymptotes. We have x equal -1. We always put asymptotes in as dashed lines. Horizontal asymptote at y equals 0. So it's actually supposed to be right on the x-axis there, but I just put it above to show so we can see it. So again, horizontal asymptotes. I could cross them, I could go through them, and then I usually come back and approach them. Vertical asymptotes, like a wall, I can't go through them. So graphically what we have is, if I were to put in some t-table values, or if you remember your parent functions for this, parent function for a 1 over x would be left 1, down 1, right 1, up 1. But all of that's going to happen from our new start point, which again, we've got an h thing happening here. We have a translation of left 1. And that, by the way, is what determines this point, the intersection of our asymptotes. And in these reciprocal functions, we call this an imaginary start point. We physically don't go through -1, 0, but we use that to base all of our movements from. So in terms of parent function notation, left 1, down 1, right 1, up 1. Those are your two generic movements, and then we just know we have branches from there. And I'm going to do all of that from right here. So left 1, down 1, puts me right about there. From 0, -1, 0, I go right 1, up 1, puts me there. And then I can draw in my branches. So we're loving on those asymptotes, but we're not going to touch the verticals. We're going to get closer and closer to those horizontals. So this is your reciprocal function or your hyperbola. That's the original function. And looking at this, I would have horizontal line test works everywhere. Even in these places where it appears the graph is going flat, it doesn't. It keeps decreasing as x gets bigger, y keeps getting smaller. So there is no place where it actually goes horizontal. So this passes your vertical line test, which means, yes, we're going to have an inverse. And again, if you're not real sure on where that graph came from, pick your own values of x and find y's. All right, so we've determined we're going to have an inverse. This thing passes the horizontal line test. So now we are to write a rule and then show that the two functions both equal x. When I have the inverse rule and the original function rule, we're going to composite them and see that we get x's. All right, we're ready to do our switch solve. So we take our original function, f of x, equaling 1 over x plus 1. And again, f of x is the same thing as y. If you wanted to just make it y. And now we're going to switch x's and y's and solve for y. So y becomes x, x becomes y, and now we solve for y. Got a little work to do here. Let's multiply both of these sides by y plus 1, y plus 1, and we get x times y plus 1 is now equal to 1. Now we divide out that x, and we get y plus 1 is equal to 1 over x. And then now we subtract the 1, and we get y is equal to 1 over x minus 1. So our inverse function is equal to 1 over x minus 1. There's our rule for our inverse function. Now we're going to test them to show that they are both equal to x. Okay, so let's composite. Let's do, first of all, we're going to composite f of x with f negative 1 of x. So we're going to be doing this f of the inverse of x. So we're going to stick the inverse function into the original function. All right, here we go. Original function was 1 over x plus 1. So we have 1 over. This is now going to come and substitute into the x. So 1 over x minus 1 plus 1. All right, what we see here is our 1 over x minus 1 plus 1. We get those 1's to cancel each other out. There you go, bye-bye. I end up with 1 over x. And that's just a reciprocal. So, multiply by the reciprocal here. You end up with 1 times x over 1, which is just x. All right. So far, we've done the composite of f of inverse of x, and we get an x, which is good. Now we're going to go the other way. Now let's do the inverse of the original function. Now we're going to composite them this way. 1 over, and then now we're plugging our f of x function in. And our f of x function was, what was our f of x function? 1 over x plus 1. All right, so I have 1 over 1 over x plus 1. And then that thing minus 1. Here's another way to look at this is maybe write it like this. F of x is 1 over x plus 1. There you go. Plugging things in. Could have done that on the other one as well. F of 1 over x minus 1. All right. A little work to do here. Got some complex fractions going on. So let me show you a quick way to think about this problem. First of all, let's deal with the 1 over x plus 1. 1 over. All right. We know that 1 over x plus 1, or maybe we don't know this. Hopefully you remember this. This is the same thing as x plus 1 to the negative first power. So I can write this as 1 over x plus 1 to the negative first power minus 1. And then when we have negative exponents and we want to make them positive, we just change the location. So if they're negative as a denominator, we will become positive as a numerator. So I can now write this as x plus 1 on the top, because I'm just taking this negative exponent and moving up to the numerator. And then there's still the minus 1 there. And look at that. Amazing. We end up with x again. So both times, when we composite one into the other, we end up with an x. And so that is the proof. There it is for showing that two functions are inverses of one another. Not the graph, but the algebraic proof of how we have two inverses that are, or two functions that are inverses of one another. So, just a warning, people are going to do some different things on this for your test question. That's what I'm looking for right there. Plugging one into the other. All right. Do a little more practice here. So we're going to show that the inverse of h negative 1x, is equal to the original function, x, h of x, if our original function is negative 2 over x. All right. So here I'm not proving that they are inverses. What I'm doing is showing that the inverse is equal to the original. And so in this process, again, I'm thinking about if an inverse means to switch the x's and y's, then I will take my original problem, h of x, which is equal to negative 2 over x, and I will switch my x's and y's, remembering that h of x is y. Then this becomes x is equal to negative 2 over y. And then we solve for y again. So we switch and solve. Solving for y, multiply both sides by y. And I would get yx is equal to negative 2. And now we divide both sides by y, or by x, excuse me. And we finally come up with our inverse is equal to negative 2 over x. And that is the same thing as our original function. So they are indeed equal to one another, both of them being reciprocal functions. Amazing. All right, not having to worry about any graphing there, but yes, those would be inverse. They are passing the horizontal line test, so they would have inverses, and it would just have to be the same thing, graphically speaking. All right, and our last one here. Y is equal to 6 minus x squared, and then now we have this new notation. We haven't seen this before. This 4x greater than or equal to 0. It also might be written in the book just like this, just with a comma after the 6 minus x squared. And this is our domain restriction. This is forcing us to look at a parabola piece so that I can create an inverse for it. If I didn't have that greater than or equal to 0, and I just graphed y equals 6 minus x squared, once again, I would have a situation where I do not have a function that passes the horizontal line test. So real quickly, if we sketch this 6 minus x squared without the domain restriction, this is a graph that is moved up vertically 6. It is flipped over because of the negative in front of the x squared, and it has your normal parent function movement. So a y-intercept at 6, left 1, down 1, left 2, down 4, right 1, down 1, right 2, down 4. So this is what my graph would look like. Something like that, without restrictions. Now this y equals x line that we have drawn in here, this guy, that's my reflection line. And when we're talking about inverses, we are reflecting them across y equals x. That's like the mirror, and we're producing the mirror image on the other side. All right, so if I had drawn y equal 6 minus x squared didn't restrict, we can see that this thing would not pass the horizontal line test. Doesn't pass, not going to give me an inverse. So what we do is we restrict the domain, and this says to only look at the x's that are positive and 0, which means we're looking at the right side of that parabola. So we're going to get rid of this other side. Now I have a graph that will pass the horizontal line test. When we create our rules for these restricted domains, we have to remember to include in my rule, when I switch x's and y's, I'm also going to switch the x and y's for my restrictions. This will tell me which part of my radical, if I have a squared function like this, which part of my radical I have to look at. Or if I had an absolute value that I was restricting, which side of the absolute value I'm going to have to look at. So this is important. When we do our switching thing, we switch not just the y's and x's of the function itself, but of the domain value. All right, the first part asks us to sketch. And again, I could write my inverse equation, and from that graph, I could do that. We just want to sketch based off of the coordinates that we currently have, and just switch those coordinates. That's, again, probably a real quick way of us generating this new graph. So let's take a look at our coordinates. Here we have 0, 6, and then we have 1, 5, and then we have, what, 2, 2? So we're going to switch those. We're going to create the new graph, the reflected graph, which will be our inverse graph. We switch x and y. So a 0, 6 becomes a 6, 0. And a 1, 5 becomes a 5, 1. And a 2, 2 stays the 2, 2. So here are our new equation, or our new coordinates. And just put a circle around that one. So my graph looks like that. There is the reflected image of the green, just simply by swapping out my x and y coordinates. It's a vertical line test passer. I can pass vertical line test. It's a function, therefore it's an inverse. So that's part A, sketching the graph. Now we get to the rule, again, another name for an equation, right? A rule for this inverse. So we're looking for, what does the inverse function look like? First, we're not going to ignore our restriction. And we're going to switch our x's and y's. So our x's replace our y's replace our x's, even in the restriction. So even that x greater than or equals 0 is now going to become y greater or equal to 0. Now we're going to solve this thing for y. So we move our x over. I like making my y's positive, so I'm going to move my y squared over here, move my x over here. Then I get y squared is equal to negative x plus 6. And y would equal greater than or equal to 0 still. All right, we're thinking about undoing a y squared, which means we're going to have to take a square root of this. So look what happens. When I take a square root, I get a plus minus answer of negative x plus 6. And let me just rewrite this a little differently. Think about, yesterday we talked about horizontal stretches and shrinks. I'm going to pull a negative 1 out of this thing and have an x minus 6 left in here. This is just taking a look at that translation part of our transformation equation we were looking at yesterday. So this is actually a shift to the right 6. And if we look over there at our graph, we do see that this graph is starting at 6 instead of negative 6. And the negative 1, what this guy's doing, the negative 1 in our equation, is saying, instead of going right, which is what we normally do with a radical function, we're going left. All my left-right movements are switching. And now I go left instead. We still have to contend with, however, this plus-minus thing. Because if I graph this as a plus-minus root negative 1 x minus 6, what I would get is a bottom part for this curve here and generate a sideways-looking parabola. So the blue part deals with, the blue part of our curve is actually dealing with the positive root. And if I were to graph the negative root, it would be this. And that's not going to pass our vertical line test. It's no longer an inverse. So what does y greater than or equal to 0 mean for this function? It says to look at the positive root. If it was less than or equal to 0, I'd be looking at the negative root. Or, if I look at the graph of it, it says I want to graph everything above y equals 0, and that's what we've done. We've graphed everything above y equals 0. So this red is not there because we, of course, are not considering the plus-minus part of it. So we can finally write our inverse as the inverse function is equal to positive root of negative 1 times x minus 6. There's my inverse. Ignoring the negative part of it. So we can see how that domain restriction comes into play when we write our rule. We have to consider that to look at which piece, in this case, of my radical function do I need to use. All right. That's all she wrote. Keep going on that.